Ladies and gentlemen, it gives me great pleasure to tell you that our next guest is not only the author of The Goddamn Fool, but also the president of the Dionysium. And his name is LBDO. And here to learn us about infinities is that guy,
Thank you, Mr. Chairman. This will be a brief lecture, but it may seem to go on forever. You get it? Now, if we're going to talk about infinities, we really need to talk about big numbers. Now, and as you probably know, big numbers are difficult to write out because they have so darn many zeros. So we have a way of doing that. Does anyone know what that way is? Scientific notation is exactly right. That's why this is the science show. Those scientific notation things are exponents, and as you can see, they correspond to the number of zeros in a number. So yeah, that's how we can get some really big numbers onto the page. And the numbers just keep getting bigger. So yeah, 10 to the 9. That's a big number, right? It's the number of grains of sand that would fit into this theater. Can you imagine that much sand? It's not easy. I can't do it. So what about the number of particles in the observable universe? Believe it or not, there's a number for that, and it's 10 to the 80. Yeah, we're talking about subatomic particles. We're talking about all the particles. Every darn particle in the universe is 10 to the 80, so that's a big number. But there's a bigger number, and we all know it. That's right, it's a googol, 10 to the 100. The googol is a number so big, well, as we've just seen, it's not only bigger than the number of grains of sand that would fit in this theater, it's bigger than the number of particles in the observable universe. Yes, there was a mathematician, as you know, who asked his nephew to come up with a name. The nephew came up with the name but spelled it wrong. So we have to thank the search engine people for fixing that. So is Google really a big number? Well, yeah. But what about a Googleplex? A Googleplex is 10 to the 10 to the 100th, or 10 to the Google power. Now, folks, that's a big number. How big? Well, let's say you wanted to write down all the zeros. You write down the 1 and you start writing the zeros. How many pieces of paper would you need? More than 4. More than all of them. I think I heard all of the pieces of paper. You would need more than all of the pieces of paper. You would need, let's say, well, it depends how big the zeros are, right? What if you wrote the zeros the size of a quark? A tiny subatomic particle. You still wouldn't have enough room in the observable universe to write all the zeros in a Googleplex. Okay? Okay. And yet a Googleplex is exactly as close to infinity as the number 1. That's right. Big numbers are not closer to infinity than small numbers, because infinity is just that crazy big. So what's an example of an infinity? Here we see the integers, the whole numbers. They go up in the positive direction. They go down in the negative direction. They go up in the positive direction infinitely, all right? But here's what's weird. What's the difference? Those are the even integers. Also infinite, but only half as large as the positive and negative integers. That's right. What you have there is two infinities, one twice as large as the other, yet both infinite. Yes, right. The mathematician George Cantor proved this in the 19th century. He loved to talk about infinities. And then there's a bigger infinities, too. Bigger than the integers. Well, you have your... you can double the number of the size of the infinity by having the 1.5. 1.5, 2, by adding the halves, right? So that adding those also doubles the size of your infinity. And then you can keep going, right? Because you add, in addition to all of the fractions, which there are an infinite number between every integer. So between 1 and 0, you have 1/2, but you also have 3/4, 1/4, and so on. That's an infinite number between 0 and 1. And then, if you add the irrational numbers, you get an even greater density of infinity, because each infinite number, each irrational number is itself an infinite number. Pi is the most famous irrational number. What is an irrational number? A number that cannot be expressed as a ratio or a fraction. That's why it's called irrational. That's where we get our word irrational and rational. Yes, the number of digits in pi, as you may know, is infinite. So you have an infinity right there on the number line in the middle of all these other infinities. So it gets a little out of hand. But what about, this is supposed to be a science show, right? Not a math show. What about the science of infinity? Well, we don't know whether there's an infinite anything in this universe. The universe may be infinite. It may be very, very large. But I found a very interesting fact. There is a size limit on the universe beyond which we will find some very bizarre results. Okay? That is the size of the universe. I'm sorry. That is the maximum number, 10 to the 70, the maximum number of possible quantum states. Okay? So what we find then is if the universe is large enough, then we get a larger number of potential quantum states, or a larger space than can be filled by that small number of quantum states. What that means is we have to repeat them. Okay? So what's a quantum state? Well, this room with all the people in it, that's a quantum configuration that would have to repeat if the universe is sufficiently large. So that means if the universe is, let's say, a googolplex meters across, then it is a fact that there have to be multiple instances of me and you, and indeed the Dionysium. And because of the Dionysium happens at the Alamo Drafthouse, there have to be multiple instances of the Alamo Drafthouse, which happens to be on planet Earth. It wouldn't work anywhere else. So there have to be multiple Earths. And we're not talking about the multiverse here. We're not talking about anything like that. We're talking about our universe, just at a very great distance. There would have to be potentially, if the universe is infinite in size, an infinite number of Dionysiums with all the people in it. Thank you. And that's it. Any questions?
Questions. We should have an infinite number of questions. Way back there.
Yes, I have a question.
Yes.
Why does it, if the universe is large enough, why does there have to be infinite copies of us? What's the proof for that?
Why do there have to be infinite copies of us? Well, again, there's a space, right? there's a set of possible configurations, including empty space, that can possibly exist, and that without any repetition. Okay, so everything that exists, including empty space, has been defined as being part of this set. And then you find out that the universe is much larger than that set. Then you have the necessity beyond that to have configurations that are not part of that set, which is impossible because this is all the possibles, or repetitions. Okay? So, I don't know.
There, yes.
So when you talk about the quantum states and that space, is every quantum state for the entire universe, or is there some space that they're defining within?
Well, are we talking about all the states for the universe? I think so, yeah. Yeah. I mean, well, no, I mean, the ideal, given a certain volume of space, you have a certain number of possible quantum states. So the number of quantum states in a thimbleful would be quite small compared to this huge number, 10 to the 70th. If you get large enough into a space, the number of possible quantum states increases with the volume of the universe, right? So the question is the universe so large that these quantum states that are potential in that volume is larger than the possible number of quantum states? And if it is, we have to have repetitions.
We can take one more question, so if your question is bad, lower your hand at this time. All right. Good questions here. I'm going to go right there.
So, if there are infinite Alamo draft houses, and there's infinite so much more, what do we have that actually is finite in a quantum universe?
What do we have that is finite? Well, I think this audience's patience is probably finite. Again, it all comes down to how large. We don't know how large the universe is, and if it is not as large, if it's approximately the size we think it might be, then this whole repetition thing is moot, because we don't think it's large enough to have this effect take place, and then everything would be finite, including the universe itself. But we don't know how large it is, and this is a great thing we don't really understand. Like we talk about the universe being finite but unbounded, or vice versa. I mean, what would the edge of space look like? What would the edge of the universe look like? Well, it's almost inconceivable, right? Some people say it's like Pac-Man, where you go through the thing and you come out the other thing. Thank you.
Dionysium President L.B. Deyo! Yeah! So what's the smallest infinity? Is it like...
There probably is a smallest infinity. I would think it would probably be like some...
I think it would be like infinity.
Infinity divided by almost infinity or something, man.
Yeah, like near infinity, that's also infinity.
Yeah, man. Listen.
Pretty cool.
I had to take algebra and algebra 2 in summer school.
You should have took infinity and infinity 2.5. I don't know what I'm talking about, man.